We are live. Welcome, you guys. This is Rachel Cassidy with the Utah Division of Drinking Water. This is our monthly webinar. Welcome to January's webinar. We made it through most of January anyway. I'm going to do just a quick review of things you need to be aware of, and then we've got our guest speaker, Dr. Carlson from the University of Utah. So hopefully we'll be able to get her most of the time. So you guys, things to know. Reminder, so we have some new staff at the division. We've hired Michelle Darris and Ryan Deering. They've started in our field services section. And so we'd like to welcome them. If you have questions about emergency response, it would go to Ryan, and then Michelle is helping us out with her expertise as well in emergency response and sampling and surface water. So we do have some people who have retired, Kim Dykes and Kate Johnson. They were both managers here at the division. They just barely retired this month in January. And then also Mark Hansen retired as well. So we're hopefully going to get some replacements. Quick reminder about the Rural Water Conference. It's coming up quickly. It's only a month away. So make sure you're registered for that, and I will be there. So hopefully you can catch me. And if you need to make appointments or anything, just email the direct people that you need to make appointments with. We'll be there all week. If you want your 2017 Consumer Confidence Report, you want help with that at the Rural Water Conference, you want to schedule that directly with Brandy Smith. And this is her number, 801-536-4210. She's making all of those appointments directly with the water operators, with you guys. So contact her. Training calendar is the same. And so check that out for your CEUs. Plan ahead. Make sure you get everything squared away before the end of the year. WaterLink is the same, waterlink.utah.gov. We did a big webinar at the end of November last year on how to navigate WaterLink. So I'll refer you to that if you have any questions on how to move around. Just go to our main website, drinkingwater.utah.gov, and the link to the webinar is at the front, the top page there. So these webinars, you can get the continuing education units for up to 6 months after the webinar airs. So you don't want to go to the April webinar last year and expect that you'll be able to get the credit for that. It has to be either 6 months old or younger in order for you to get the CEUs. And then, that doesn't show up. There it is. CEU information, you should email your CEUs to our new CEU address, ddwceus@utah.gov. So, all right, that's enough of me. Fast and easy. Okay, so we are so excited to have Dr. Krista Carlson from the University of Utah. She's a professor there, and her research focuses on, we didn't get all of it.
Nope.
It's a brand new page, so that's the best way to summarize it.
Yeah. That was our Google Fu presenter bio.
Yeah, so her research focuses on new and innovative water treatment processes. So we're going to switch to her presentation. It's much more exciting than mine.
Yeah.
All right, Krista, take it away.
Thank you. This is my first webinar, so this is very exciting. So my background is in material science, and right now, one of the things that we're working on are point-of-use titanium dioxide-based reactors for the disinfection of waterborne pathogens. And this could be used domestically, and we're also looking at different areas overseas. So for the overview, I'm going to spend a little bit of time in the beginning discussing advanced oxidation processes, a little bit about materials properties, why can we use titanium dioxide for water purification, why we grow nanotubes and use them versus nanoparticles. And then the majority of the talk is going to be focused on the properties and performance of this titanium dioxide-based disinfection device. So starting off with something that you are all very familiar with, more than me, common drinking water disinfection methods. And two of the most common are chlorine and chlorine dioxide, which are typically introduced as gases. Same with ozone. And in these cases, you're producing reactive oxidants that then interact with pathogens, leading to inactivation and or cell death. When UV is used as the primary form of disinfection, we are now targeting the DNA. And there's also some damage to the cell membrane, but really what we're trying to do is inhibit the repair and replication of the pathogen, which eventually leads to disinfection. And in the titanium dioxide reactor, we will be discussing producing oxidants just like with the chlorine and ozone. And during oxidation, there's a transfer of electrons from one species to another. And you can also transfer oxygen from one species to another. And for example, if you have chlorine gas introduced into the water, it can hydrolyze to form the oxidant hypochlorous acid. Similarly, when ozone is introduced into the water, you can get the superoxide ion or hydroperoxyl radicals. And depending on the pH and other species in the water, these reactions will occur. But the main point is that either the original gas that's introduced into the system or the radical products can interact with the cell, causing physical damage to the outer membrane and or structural changes within the plasma membrane, and both of these can lead to pathogen death. So these oxidants can also oxidize the cell lysate or internal components of the cells, which is good because upon cell death, some of these toxins can be produced. And why do we care about finding new methods of oxidation? Well, because not all oxidants are created equal. Some are stronger than others. The oxidizing or reducing character of any chemical species is given by the standard redox potential, as shown in this table. And notice that chlorine and chlorine dioxide have lower oxidizing potentials than ozone. This means that for a given concentration or type of pathogen, it might take a longer time or higher concentration of the species with a lower redox potential to kill the pathogens than one with a higher. And if you note that the hydroxyl radical is the strongest. So due to the fact that you want to maximize the disinfection power, as well as the fact that some pathogens like cryptosporidium are becoming resistant to weaker oxidants, advanced oxidation processes are being examined. And advanced oxidation processes are ones in which oxidation occurs primarily through reactions with hydroxyl radicals. So in the technique, you want to directly produce hydroxyl radicals or have them produced somewhere in the propagation reactions of the radical chain. Established reactions that you might have heard of are some combination of hydrogen peroxide, ozone, and UV light. And an emerging technique that has actually been around for decades is the use of titanium dioxide and UV light to directly produce hydroxyl radicals. So how does this work? Well, before we start, we need to understand a little bit about materials and how they react to external stimulus. In a metal, the solid is composed of atoms that all share their outermost electrons or valence electrons. And these electrons can easily be accelerated in the presence of an electric field. If in water, the applied voltage is high enough, then these electrons can interact with the water species and cause the production of hydrogen and oxygen gas. If we have a semiconductor, now the electrons are bound more tightly to the atoms, and it takes a little more energy for them to flow. But once they do, they leave behind a positively charged space, which we call a hole. And this hole can act as a very strong oxidant. This electron hole pair can be created by the input of some kind of external energy in the form of an applied voltage or light. And that's what we use for titanium dioxide very often. UV light is irradiated on the sample and provides enough energy to enable the creation of this electron hole pair. Now, if these charge carriers can reach the surface of the material before recombining with one another, and they are able to interact with the water species, this can lead to the direct production of radicals. So if the electron reacts with oxygen, it can lead to the superoxide ion radical, and the hole can actually cause the direct formation of hydroxyl radicals. And then both of these can also lead to the formation of additional radicals. And so we utilize this concept in our original water purification device. This is our original prototype for a personal point of use water disinfection device. And for this, we took a titanium wire and grew titanium dioxide nanotubes all over the surface and placed it in the serpentine channel you can see on the left. And the electron hole pairs were created as we irradiated the sample with simulated solar. And we ended up applying a small voltage to the system using the titanium wire as an anode and the stainless steel backplate as a cathode. And this helps to keep the electrons and holes from recombining with each other so they can interact with the water. So as the pathogens were gravity fed through the system, they would be physically destroyed due to the production of radical species. So one thing to point out is that we used nanotubes that were grown on the surface of titanium and not nanoparticles that you typically interact with in white frostings, toothpaste, paints, vegan cheese. And this is all because of several reasons. First, it's really challenging to use nanoparticles. These are particles that are 1,000 times smaller than your hair. So trying to use them and filter them from the water you just cleaned would be a challenge. And the nanotubes don't have this issue. They're grown on a titanium substrate, and it's a very strong bond, so it's easy to use and reuse. Additionally, I had mentioned that we were applying a voltage to the system, and we want the electron to be able to flow from the titanium dioxide into the titanium with as little resistance as possible so you don't get that recombination with the hole. The nanotubes, you have a straight shot from the nanotube into the surface of the titanium, while with the nanoparticles, you have a more tortuous path. The electron has to cross an interface between particles, and this can be a challenge. And this can lead to more recombinations with the holes, so there's not as much oxidant to interact with the water and produce the radicals. We utilize this semiconducting nature of the titanium dioxide for other applications in the lab. So we also look at the purification of organics in water and also organics and pathogens in air. We also use the nanotubes for disease diagnostics from the breath. So certain diseases will cause breath markers, and then we can detect these diseases immediately instead of having to wait a long time for the results from complex tests. Additionally, we can grow these oxide layers on metals to help with the incorporation of the metal implants in the body. So how do we grow these? Well, we use a process called anodization. And this means that we make the titanium substrate the anode, place it into an etching solution, and apply a voltage. Now we typically apply 30 volts and use platinum as the cathode. And during this process, the titanium gets etched and reacts with oxygen in the solution to form titanium dioxide nanotubes, which are very strongly chemically bound to the surface of the titanium. Here's a scanning electron image of these tubes. And really this process of creating the hydroxyl radical could come from just a solid titanium dioxide sheet. But having all of these little tubes creates a very high surface area, so you get a greater production of the radicals. Now we do some post-formation processing to enhance the generation of radicals. We put the sample into a furnace and we heat treat them, a process which is called annealing. And in this process, we can use different gases to get different properties. So in our case, we want to cause the titanium dioxide to be more conductive, and we wanted to be able to absorb more visible light to enhance the radical generation. So if we anneal samples in air, we make them fairly resistive. And if we anneal in other gases like nitrogen or hydrogen, this imparts defects into the structure, which increases the conductivity and absorbance in the visible spectrum. So here's a photo of those samples. And the first thing you'll notice is the color difference. The darker color means that we are absorbing more visible light. So to quantify this, we did UV visible spectrophotometry. And all that means is that we just measured the absorbance at different wavelengths. And we can see that we are getting more defects in the hydrogen annealed samples, and that's giving us a greater absorbance in the visible spectrum compared to the air and nitrogen annealed samples. And this should help us produce more radicals. And that's what we found after testing our device with E. coli that we grew in the lab. So we looked at different lighting conditions. 25 milliwatts per centimeter squared is a cloudy day, while 100 milliwatts per centimeter squared is a sunny day. And we also looked at different voltages. The red column is the original solution containing the bacteria. The orange is the bacteria concentration after passing the water through the device with no applied voltage. And then the remaining columns are different voltages up to 3 volts. And what we noticed is that sunlight didn't have as much of an impact as we thought it would on the bacteria side or cell death. In fact, at 3 volts, complete cell death occurred regardless of the lighting conditions. So it could be dark or a fully sunny day, and it didn't matter. So the devices containing air and nitrogen samples, which were not shown here, the data, never showed any cell death, complete cell death, regardless of the applied voltage. So we needed that hydrogen annealing to give us that defects in the structure. So now we know that chloride ions could also be affecting this result. And we know this because it can react with the titanium dioxide to produce chlorine radicals. And this is the data from different salt concentrations with only an applied voltage, but with no simulated solar irradiation. And as you would expect, the higher salt concentration did give a greater effect on bactericide. But again, we also saw that we could get complete cell death in dark conditions and lower concentration of salt if we just ramp the voltage up high enough. So for 1,000 ppm, where you have more chlorine radicals, complete cell death occurred at 2 volts, while for a salt solution with very little chlorine radicals, you had to increase the voltage to 5 volts. And these results were quantified using plating. So we took a small sample from each of the original solution and the effluent, and we'd spread it around the plate, put it in a warm environment for 24 hours, and then come back to count the dots, called colony forming units. And what we found is that regardless of the water conditions, we got no growth when 6 volts was applied to the sample, meaning that we killed all of the bacteria. And this was in simulated waters as well as those I collected from various ponds and streams in the area, first filtering the water and then spiking it with our bacteria. And we did this, we filtered out the natural bacteria because not all of the natural bacteria would be grown on these plates. So to examine this phenomenon a little more, we looked at how the material behaved when they were exposed to the simulated sunlight under no applied voltage and also under an applied voltage. So starting with just the behavior with sunlight and 0 volts, this test that you're seeing the data for shows the current density over time. So when we switched the light on or the solar simulator on, you see an increase in the current density. And when we shut it off, it would drop back down to 0. And this is due to the fact that when you switch the light on, you are forming these electron hole pairs and you're getting more charge carriers that can interact with the water. So you can see that the nitrogen annealed sample actually shows a better response than both of the hydrogen and air annealed samples. And this is due to the fact that we have created so many defects in the hydrogen annealed sample that the electron hole pairs are created, but they recombine before being able to interact with the water species at the surface. The air sample is lower because of the crystal structure of the material. It makes it less conductive, so you don't have as many charge carriers that are forming. But when we apply a voltage to the system, now the hydrogen annealed sample gives a much higher current response. and the effect of sunlight is actually minimal. So what this is showing us is that we can get a significant amount of charge to interact with the water, but are we creating radicals? To visualize this, we use what's called DPD dye. And this is a dye that just turns pink in the presence of radical species. And for this device, we had a whopping 50 milliliters per minute flow rate, which provided a 15-second residence time. And we applied 6 volts to the system with no solar irradiation. And what we saw was that this clear solution turned pink as it flowed through the reactor, meaning that we were creating radicals. And we also didn't see any bubble formation, meaning that the water splitting, if it was occurring, was minimal. And we are dealing with pretty low currents as well, typically 5 milliamps at most for natural waters. To quantify this, we put the dye in the UV-Vis spectrophotometer and measured the absorbance. A higher absorbance value indicates more radicals were forming. And the hydrogen annealed samples shown in pink there, they have a much higher absorbance than the other samples. And this is starting at 3 volts, which is where we had observed complete bactericide in the past. And notice in the image, the pink dye is forming around the nanotube coated wire. And what we learned shortly after this test is that at any flow rate greater than 50 milliliters per minute, cell death was actually the result of direct interactions with the nanotubes, not hydroxyl radicals that were forming in solution. So this finding enabled us to change the design and create a device with higher flow rates. Currently, we are in the process of using bleach and ozone to try to quantify the disinfecting power of this material. This is some data from Immigration Creek. We also looked at Liberty Park Pond. I collected the samples right behind the geese, so they were nice and fully loaded with coliform. This data was generated by Chemtech Ford, a local independent laboratory. And we found that we could still kill all of the bacteria at 6 volts. We just needed to have a longer residence time in the system. And this makes sense because the bacteria we grow in the lab are pretty weak compared to natural bacteria that probably experience a lot more flux in temperature. There's also different inorganic and organic compounds that we weren't simulating in our solution. So for our new disinfection device, we actually have increased the residence time to 90 seconds just to ensure that everything is dead. But we wanted to also examine what is physically happening to the pathogens as they pass through the reactor. We know that they die, but are they physically destroyed? And to confirm this, we used flow cytometry, which uses scattering and fluorescence to tell us about the size of a particle. For example, if we start with a particle that is 5 microns, we can tell if it has been shredded to less than this size from this data. So if we look at this graph, the red peak is the result of the original bacteria that we grew in the lab. And the pink is the result of smaller debris from either already dead cells or salt in the water. And after only 15 seconds in the device, there is really very little sign of whole cells, and the debris peak has increased, meaning that after only 15 seconds, we are seeing physical destruction of the cells. And this increases as we increase the time to 5 and 15-minute treatments.
Brutal.
Yeah, no, exactly.
Complete destruction.
See the images. And the most important part about this is that we're really going to be going after some more challenging pathogens like Cryptosporidium or Giardia. And this is, these are some scanning electron microscopy images of the pathogens before and after going through the electrocatalytic reactor, which is our titanium dioxide-based device. And before you can see the cells, and after the treatment, it was very hard to find pieces, but if you did find them, they were smaller. The Giardia just kind of looked shriveled, not as torn up as the bacteria, which makes sense because it does take a little more time to break that cell wall down. And so based on this result, then we redesigned our reactors so we could make a residential scale system. So this now looks like a bunch of nanotube spirals, I'll show in a second, that are put in a pipe. And basically you're just putting the water in. We no longer need sunlight. You're applying 6 volts to the system, and then usually a maximum of like 5 to 10 millivolts, and you are killing the pathogens by direct interaction with the surface. So this can be run off of a rechargeable solar battery. If we want to scale this to a community scale, we had to do some testing, and the left is what we're 3D printing and we hope to be making soon. On the right is the hard work of our undergraduate students, anodizing wires and then weaving. They're really good at weaving. Arts and crafts are important for science.
Yes. Take those classes.
Exactly.
Basket weaving was the like throwaway class, and now it has significant value.
And so they wove a bunch of these discs, and we put it into our prototype, our small scale prototype. And it's still, we have a 90-second retention time, but we can still kill 10 to the 6th CFU per milliliter with the bacteria that we grow in the lab in 15 seconds. So the benefits of this disinfection technology, we get chemical-free oxidation. So you are creating the strongest radical species without having to introduce any gas, which is actually really nice because it's basically temperature independent. We just have to be between freezing and boiling, and we can create these radicals. And that was my second point. Yeah. Okay, so the most powerful form, and it's more simplistic than other comparable technologies. So you can run it off a solar charged battery pack. There's very few moving components. It's very simplistic, which is good if we're going to deploy these systems in rural communities, which is also why they need to be durable and chemically inert. So you're basically putting a ceramic, like a bowl. This is what this titanium dioxide is. It's very strong, so it's good for remote settings. And we can potentially recycle it, so you can send in the titanium and you can remove the nanotubes and grow them again. We've been working with places in rural India. So they have systems that remove turbidity and iron, but we have a partner that can help remove heavy metals. There's a problem with arsenic. And then we will put the reactor after that. So we destroy the pathogens. And then we have a partner that's also working on pathogen sensing. We've also been working with the U.S. Centers for Advanced Studies in Water. Sorry, I'll get some cleaner slides, the transfer from the Mac to the PC. But with this program, my newest grad student is down in the right-hand corner there. He came from this program, and we've been working on trying to figure out a way to make this system be useful for urban Pakistan. So they have problems with getting clean water and energy. So this system would be combined with a small vertical axis wind turbine that they could put on the roof. And over half of the water supplied to one of their largest cities on a daily basis is unfiltered. And water contamination actually accounts for 40% of all the deaths. So having these systems is really important in places that are still working on their infrastructure. And that's it. I'd like to acknowledge my colleagues, Sarmitra Mohanty and Mano Misra at the University of Utah, all the wonderful students that we've had working on the projects over the years, and our funding agencies for their financial support. Thank you.
Thank you. We do actually have questions, which never happens. So I know.
I hope I can answer them.
I know. They're like, how soon can we get it? How much does it cost?
Yeah. I heard 3D printing in there. Can I just make this at home? Is there anywhere of the treatment matrix, such as the titanium dioxide dislodging?
One of the things that's a great question, because that's the issue with nanoparticles, right? How do we adhere them to the surface? How do I go back without making everyone sick here?
It's Monday. Everybody's a little sick anyway.
Okay,
we show up a little disoriented.
So that's one of the biggest problems that we have with using nanoparticles is that if you were going to put these onto a substrate, you would have to have some type of binder, and that wouldn't be as robust. The way that we make these nanotubes, they are chemically joined to the metal substrate. And so they have a very strong bond and they aren't easily removed. You can try to scratch these off, and that's really the only way. You have to really physically remove them. You can apply a cathodic bias to the system, and that can eventually pop it off, but we wouldn't be doing that. But one of the things we do, it's called dynamic light scattering. And after we run a sample through, we just run DI water through the device and we apply a voltage, and you can take the water, put it into this dynamic light scattering system, and you can tell if particles have come off. And we haven't seen anything so far. We've run about over 1,000 liters through one of our small scale devices, and it still seems to be okay. We also removed the titanium at some point. I have a slide. Oh, wait, here, if I hide this. We look at what voltages we want to apply. The reason why we want to apply 6 volts is it's easily manageable. It gives us a small current. If we do start to go to higher voltages, if you see here in 100 ppm salt solution, we are getting a significant amount of current. We start getting above 50 milliamps, and at 7 volts after 45 minutes, you can see, can they see my arrow or no? Maybe.
Mm-hmm.
Okay.
Yeah, I can.
So you can see that the nanotubes do come off. But at 6 volts, we've now run this consecutively for 5 days straight, and we haven't seen any removal. Wow. So we have to test the balance, but.
That's cool. And then one other question, could this process eliminate iron bacteria as well?
Iron bacteria? I don't know what that is. I'll have to look that up. So if it can be oxidized, then in theory, we should be able to destroy it. So with organics, it becomes more challenging because sometimes the organics will degrade into something that wants to adhere to the surface of the nanotubes. But with a bacteria or pathogen, I'm thinking that it might be possible.
Yeah.
It says bacteria in there, yeah.
When there is wear, if there is, what size, I mean, when vessels were breaking off, what size of debris are you getting? Is it anything that would?
And so that's the interesting part with the nanoparticles, and that's why this material is so great, because with frostings or toothpaste, they use titanium dioxide all the time. So we're actually ingesting quite a bit of nanoparticles depending on our diet. And that's becoming an issue, I think, with water treatment, is that these pharmaceuticals or personal care products and nanoparticulates are showing up more in the water. So it is becoming a concern, and we don't necessarily want to pump more junk in if we don't have to. And so it can range anything from microns down to these nanotubes here that we grow are about 2 microns in length and 70 nanometers in diameter. So you can get small nanoparticles, but they don't tend to break off as tubes. They actually tend to dislodge like a sheet like we saw on those other ones if they come off.
So that's a question. What kind of integrity testing would be done to make sure that the process is at maximum effort? At what point would a home user or a community be able to say, okay, we need to replace?
Yeah, and that was actually something that was funny when we were trying to get the product out. We're going to get National Sanitation Foundation approval, so we can send the product in and they will vet it for us. What we found was interesting is that you could sell a product, these smaller scale or community scale systems, without having it go through these certifications. Not for
but not for the
drinking water. Not for drinking water, but for a personal use. You don't actually have to get this. But we would have the National Sanitation Foundation, and then we would do those tests like that dynamic light scattering to see if particulate is coming out. We can also do adhesion tests, so you can see how much force it would take to rip it off, and then how much voltage or current needs to be applied before it starts to degrade the material.
Excellent. And then I'm sure, there's so many things that are dependent on this question, including money and funding. But what's your time frame to be able to have this more widely available and applied in more communities, more homes?
We have been applying for more funding. So we have our pilot test, or we have our pilot product here. And we are ready to start testing. We do just need a little more funding, but I think we're definitely ready for bacteria in the near future. And then if we can get a lab to do the Giardia and virus testing, then I would like to say within 2 years, that's our plan. If we were a company, we try to be. So, but as soon as we can build the pilot scale and go to a test site, we have a partner that has some sites in Nevada and in the Central Valley in California. So we'd like to put a pilot reactor at both of those sites and see, and then after maybe a year of testing, then hopefully we can.
So has there been any disinfection byproducts testing from this? I would imagine there's not a lot with oxidation, but there's some ozonation that can cause like bromate. But we had one question that was if there are any disinfection byproducts.
And that's what we'll have to look at. It's hard to, so when you put the gas into the system and really then you get the chain reaction of ozone and then it breaks up. And with this now we're finding with the higher flow rates that we'd actually be looking at, you have to interact, the pathogen has to interact with the surface of that material, and you don't get any residuals that come off. But if you had some bromates or something else in the water, you would potentially have that.
And then I wonder if there's application. Have you looked at like for harmful algal bloom or cyanobacteria and cyanotoxins and the impact there?
That's it. Yeah. And that's one of the things that we've been looking at. We just set up our BSL2 or our biology hood that we're going to be using. And so we'll look at
Nice. Well, very cool. Thank you.
Thank you.
This was
Thank
great.
you so much.
Thank you for having me. This is great.
Yeah, so for the water operators listening, you'll be able to access the quiz just below the link on YouTube to be able to get your CEUs. And the next webinar is going to be just in 2 weeks. It's on Monday, February 12th at 11 a.m. And Shannon from the Rural Water Association will be here to review the conference at the end of February. So make sure you tune into that. And you guys, thanks for attending. Make sure you get your CEUs and we'll see you soon.
Yes.
And
Thank you all.
Thank you.